For decades, humanity's most advanced telescopes were aimed at the farthest reaches of the cosmos. We sought out the mysteries of black holes, charted the deaths of distant stars, and tried to map the very edge of what we could see. Yet, in all that time, we overlooked what was right next door. Just over 4 light-years away lies Alpha Centauri, the closest star system to our own. Despite its proximity, it remained largely unexamined. The glare from its 3 stars was too intense, too close, making it nearly impossible for older telescopes to see anything nearby. It was like trying to read a book while staring into a spotlight. Hubble barely managed a glance. Most astronomers simply passed it by, convinced that the brightness would drown out any hope of discovery. That changed with the James Webb Space Telescope. Unlike its predecessors, Webb is designed to see in the infrared, detecting heat signatures invisible to the human eye. It can peer through dust, cut through glare, and reveal what's hidden in the cosmic fog. In December 2023, Mission Control sent new coordinates to Webb, not to a distant galaxy, but to Alpha Centauri just 37 light-years from Earth. If you could walk there at a steady pace, it would take you about 80 million years. That's how close it is in cosmic terms. The first image took 14 hours to collect. Scientists expected to see a clearer view of Proxima Centauri, the smallest of the 3 stars, and perhaps confirm the existence of known planets. Instead, the data revealed something entirely unexpected in the region where life could potentially exist around Proxima. There was a clear, unmistakable signal, confirmed by 3 different instruments. Dr. Sarah Chen at the European Southern Observatory was the first to receive the data. She checked her calculations repeatedly before calling her supervisor in the middle of the night. "We have a situation," she said, "not because the data was flawed, but because it was accurate and it didn't make sense. The signal appeared in the mid-infrared range between 5 and 12 micrometers. This part of the spectrum is crucial for understanding what gases make up a planet's atmosphere, what temperatures are present, and what chemical reactions are taking place. Webb's instruments picked up details no one had anticipated. The planet Proxima Centauri B wasn't just sitting in the so-called habitable zone. It showed signs of an active atmosphere with temperature differences, pressure changes, and heat patterns that suggested real weather systems. There were clouds forming and dissipating, and even hints of a water cycle. Proxima Centauri B was first discovered in 2016 using the radial velocity method, which detects the tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. Scientists had already calculated its mass, its orbital period, and its distance from the star, just over 11 days per orbit and about 1.3 times the mass of Earth, right where liquid water could exist. But until now, no one had seen its atmosphere. The new data showed a vertical structure in the atmosphere with different temperatures at different heights. On Earth, this happens because of complex interactions. Sunlight heats the surface, gases rise and fall, moisture moves, and chemical reactions take place. Seeing this on Proxima B meant the planet was not just a lifeless rock, but a dynamic, changing world. But the surprises didn't stop there. The brightness of Alpha Centauri's 3 stars had always been a problem for astronomers. Point a telescope at something that bright, and all you get is glare. Alpha Centauri A is brighter than our own sun, and even from 25 trillion miles away, it's visible to the naked eye in the southern hemisphere. Alpha Centauri B is almost as bright, and together they orbit each other every 80 years. Proxima, the red dwarf, is smaller and dimmer, but still bright enough to hide any Earth-sized planets in its glow. The Hubble Space Telescope tried to look in 1995, but all it saw were 2 bright blobs, no planets, no details, just overwhelming light. Ground-based telescopes fared even worse. The Earth's atmosphere distorts starlight, and water vapor scatters infrared signals. By the time light from Alpha Centauri reaches a telescope on the ground, it's been blurred and scrambled, making detailed observation impossible. The invention of the coronagraph changed things. This device blocks out direct starlight, creating an artificial eclipse inside the telescope. Early versions didn't work well. Light would leak around the edges and the glare would still get through. But modern coronagraphs, like the one on Webb, are designed specifically for infrared wavelengths. They block visible light but let heat signatures pass through. For years, scientists debated whether Alpha Centauri was worth the precious observation time. Telescope hours are limited, and thousands of proposals compete for each slot. Why spend time on a nearby star when there are distant galaxies and black holes to study? The argument shifted in 2022 when computer models suggested that Proxima b might be able to hold onto its atmosphere despite the frequent flares from its red dwarf host. Maybe it was worth a closer look. The Webb team allocated 14 hours for a single observation window, timing it during one of Proxima's quieter periods. Red dwarfs are notorious for their violent flares, which can strip away planetary atmospheres, but they also have calm phases. Webb caught one of these windows, perfect timing, perfect conditions, perfect data. Webb's infrared approach solved all the old problems. It detects the heat given off by planets themselves, not just the light reflected from their stars. The coronagraph blocked out the three stars, and the sensors locked onto the cooler targets. Suddenly, after decades of being blinded by glare, scientists could finally see what was hiding in our own cosmic backyard. What they found was not just a single planet, but a system far more complex than anyone had imagined. The presence of three stars in one system breaks the old rules of planetary formation. Previous models said this kind of arrangement shouldn't work. Too much chaos, too many gravitational tugs, too much radiation. Planets need stability to form, and Alpha Centauri seem to offer none. Alpha Centauri A and B orbit each other in an elongated path, sometimes as close as the distance from Earth to Saturn, sometimes as far as Pluto. This creates a constantly shifting gravitational environment. Proxima sits much farther out, and some astronomers even question whether it's truly part of the system or just passing by. This uncertainty matters because it affects how planets form. When stars are born, they collapse from clouds of gas and dust, forming a disk where particles collide and stick together, slowly building planets over millions of years. But this process needs a stable environment. Change the gravitational field too much, and collisions become destructive. Three stars mean three gravitational fields, three sources of radiation, three stellar winds. Early computer models said planets couldn't form here. The environment was too violent. But the discovery of Proxima b in 2016 forced scientists to rethink everything. If one planet could survive, maybe others could too. Maybe what looked like chaos was actually a different kind of order. Webb's observations revealed that the three stars likely formed together, but Proxima drifted away early, giving each star its own zone for planet formation. The surviving planets occupy stable regions, safe harbors in a turbulent system. Webb detected these zones in the infrared, revealing where dust collects, where gaps appear, and where gravitational resonances create structure. The system looks organized now, but that order came at a cost. For every planet that survived, many more were probably ejected into interstellar space. The lucky ones remain, and they hold more surprises than anyone expected. Proxima b's numbers are more than just statistics. They're a source of hope. At 3 times the mass of Earth and orbiting just 5 million kilometers from its star, it completes a year in only 2 days. These figures place it squarely in the region where liquid water could exist, the so-called habitable zone. But red dwarfs like Proxima Centauri complicate the picture. They burn much cooler than our sun, with surface temperatures around 3000 Kelvin compared to the sun's 5700. That means any planet hoping to stay warm enough for water must orbit extremely close, almost hugging its star. Too far and it freezes, too close and it risks being scorched. This proximity brings its own set of challenges. Tidal forces from the star are so strong that they likely lock one side of Proxima b in perpetual daylight, while the other side is plunged into endless night. This is called tidal locking, and it's a common fate for planets orbiting close to their stars. Our own moon is tidally locked to Earth, always showing us the same face. Mercury nearly shares this fate with the Sun. On Proxima b, one hemisphere would be baked under constant starlight, while the other would be frozen in darkness. For years, scientists debated whether such worlds could support life. If one side is always hot and the other always cold, where could life possibly thrive? Computer models offered a possible answer: A thick enough atmosphere could transport heat from the day side to the night side, smoothing out the temperature extremes. Winds could carry warmth, and ocean currents could help distribute energy. The planet wouldn't need to spin, it would just need a robust atmosphere to keep things moving. Webb's data provided the first real evidence of this process in action. Temperature readings showed that the day side of Proxima b hovered around 300 Kelvin, warm, but not unbearably so. The night side dropped to about 230 Kelvin, cold but not frozen solid. The most interesting region was the terminator, the boundary between day and night, which stayed at a comfortable 270 Kelvin, right in the range where water could remain liquid. This temperature gradient was a clear sign that the atmosphere was doing its job, moving heat around the planet. Without an atmosphere, the day side would be a furnace, reaching 600 Kelvin, while the night side would plummet to 50 Kelvin. Only a thin ring along the terminator would be habitable, but Webb's observations showed that the heat was more evenly spread, suggesting active atmospheric circulation. The planet's gravity plays a crucial role here. With 3 times Earth's mass, Proxima b has about 20% stronger gravity, which helps it hold onto its atmosphere against the relentless assault of stellar winds and radiation. Proxima Centauri is notorious for its flares, bursts of X-rays, and ultraviolet light that can strip away a planet's atmosphere over time. Lighter planets lose their air quickly, but Proxima b sits right at the threshold, just massive enough to hang on. Scientists ran the numbers to see how long Proxima b could keep its atmosphere under these harsh conditions. The results were surprising. The planet could retain its air for billions of years, possibly as long as 4 billion, especially if it has a magnetic field to help shield it. That's plenty of time for complex chemistry to develop, and maybe even life. But the real shock came from what Webb found in the planet's atmosphere during its first observation run. When light from Proxima Centauri passes through the planet's atmosphere, certain wavelengths are absorbed by different molecules, leaving dark lines in the spectrum. By reading these lines, scientists can determine what gases are present. Webb's near-infrared spectrograph captured the planet as it transited in front of its star, allowing starlight to filter through the edge of the atmosphere. The resulting spectrum made researchers sit up and take notice. 3 distinct absorption features appeared, corresponding to oxygen, water vapor, and methane. All 3 were present in significant amounts. Dr. James Peterson at MIT was among the first to analyze the data. He ran the numbers multiple times, convinced there must be a mistake. The signals were too clear, too strong, but every check confirmed the result. Water vapor in an exoplanet atmosphere is no longer a novelty. Webb has found it on many worlds. But the concentration on Proxima b was remarkable, 7 parts per thousand in the upper atmosphere, compared to Earth's average of 4. This planet had more atmospheric moisture than our own. The presence of oxygen was even more puzzling. There are 2 main ways to get oxygen in a planet's atmosphere: through chemistry or biology. Chemistry can do it if there's enough ultraviolet light to split water molecules, allowing hydrogen to escape and leaving oxygen behind. But Proxima Centauri emits less ultraviolet than our Sun, not enough to account for the observed oxygen. Yet there it was. Methane complicated things further. On Earth, methane and oxygen don't coexist for long. They react and destroy each other. Finding both in significant amounts means something is constantly replenishing them. On our planet, that something is life. Plants produce oxygen, microbes generate methane. Chemistry alone tends toward equilibrium, but life creates a disequilibrium, keeping both gases present. Of course, this isn't proof of life. Scientists are cautious. One spectrum could be a fluke, an error, or an artifact. The Webb team scheduled follow-up observations, capturing 6 more transits over 8 months. Each new data set reinforced the original findings. The mystery deepened. Proxima b's atmosphere should have been stripped away by flares, yet it persisted, rich in water vapor and oxygen. Red dwarfs like Proxima are violent stars. Their flares can increase brightness by 20% in an instant, flooding nearby planets with radiation. Proxima b sits just 5 million kilometers away. When a flare erupts, the planet is hit in just 25 seconds. The energy is enough to blast away thousands of tons of atmosphere. Models predicted that water vapor should be gone within 50 to 100 million years, yet Proxima b is at least 5 billion years old. The atmosphere should be a thin wisp, but Webb found it robust and thriving. Something was protecting this world. The first theory was a magnetic field, like Earth's, which deflects solar wind and channels charged particles toward the poles. Maybe Proxima b has a similar shield. Another idea was that the planet constantly replenishes its atmosphere through volcanic activity or chemical reactions. Or perhaps the models were simply wrong, and atmospheric escape happens more slowly than we thought. Webb's observations offered clues. During one transit, Proxima erupted with a moderate flare. The telescope caught the event and watched how the atmosphere responded. Instead of being stripped away, the upper layers absorbed the radiation, heavy molecules rose to block the energy, and the atmosphere quickly returned to normal. This resilience suggested a dynamic, self-protecting system. If Proxima b's atmosphere can survive billions of years of flares, it might remain habitable despite the violence of its star. But this resilience raised new questions. How does a planet develop such effective defenses? Is it just luck, or is there something more at work? Patterns in the data hinted at organization, not randomness. And as Webb continued to observe, even stranger discoveries began to emerge. Magnetism is a silent guardian for life. On Earth, our magnetic field acts as a shield, deflecting the solar wind and cosmic rays that would otherwise strip away our atmosphere and bombard the surface with deadly radiation. Without it, our planet would be as barren as Mars, its air long since blown into space. For Proxima b, orbiting so close to a tempestuous red dwarf, a magnetic field isn't just helpful, it's essential. The flares from Proxima are far more intense than anything Earth experiences, and without protection, any atmosphere would be lost in a cosmic blink. The James Webb Space Telescope can't measure magnetic fields directly. Magnetism doesn't show up in the infrared or visible light, but it can see the effects. During one observation, Proxima unleashed a powerful flare, a Class M event that increased the star's brightness by 15%. The charged particles from the flare raced toward Proxima b, and Webb watched as the planet's atmosphere responded. Auroras erupted not just at the poles, as on Earth, but across the entire day side. This was a glowing shield, a sign of a magnetic field far stronger and more extensive than our own, perhaps 3 to 5 times as powerful. On Earth, auroras are confined to the polar regions because our magnetic field channels charged particles there. But on Proxima b, the auroras spread across the hemisphere facing the star, suggesting a magnetic field that envelops the planet in a protective bubble. Scientists calculated what this would require: a liquid metallic core like Earth's, and some form of rotation to generate a dynamo effect. But Proxima b is likely tidally locked, with one side always facing its star. No rotation, no traditional dynamo, so how does it maintain such a strong field? The answer may lie in tidal flexing. As Proxima b orbits its star, gravitational forces could squeeze and stretch its core, generating enough movement to sustain a magnetic field. This would be a different kind of dynamo, powered not by rotation but by the constant tug of its parent star. The magnetic field could explain why Proxima b's atmosphere persists despite the onslaught of flares. It deflects the worst of the radiation, slows the loss of lighter gases, and allows the atmosphere to remain thick enough to transport heat around the planet. This discovery elevated Proxima b from a mere curiosity to a world of extraordinary interest. A tidally locked planet with a powerful magnetic shield, an atmosphere that survives against the odds, and a climate that seems stable despite the chaos overhead. If life exists there, it has a fighting chance, but Proxima b isn't alone. Further out, at about 1.5 astronomical units from the star, roughly the distance from Mars to the Sun, another planet orbits, Proxima c. This world is colder, with surface temperatures around 150 Kelvin, far below the freezing point of water. It was detected through its gravitational pull on Proxima, a subtle wobble that revealed its presence. Initial estimates put its mass at about 7 times that of Earth, making it a super-Earth or a mini-Neptune. Its year lasts 5.2 Earth years, long enough that previous observations hadn't caught a full orbit. Webb's infrared eyes confirmed Proxima C's existence and revealed something unexpected. It, too, has an atmosphere. At such low temperatures, most gases should freeze out, but Proxima C's atmosphere is kept warm by greenhouse gases like carbon dioxide and methane. The result is a temperature inversion with a cold surface and a warmer upper atmosphere, a strange but stable arrangement. Models suggest Proxima C formed farther out as an ice giant and migrated inward over millions of years. Its current position is inside the system's frost line, where water should be vapor or liquid during planet formation. The migration likely involved gravitational interactions with Proxima b, the two planets exchanging momentum and settling into their current orbits. Webb also detected a faint ring system around Proxima c, composed of ice and dust, stretching from 40,000 to 80,000 kilometers from the planet. These rings are thin and barely visible, but they scatter infrared light in predictable patterns, confirming their presence. The discovery of Proxima c and its rings doubled the known planets in the system and hinted at a more complex planetary family. Proxima c is too cold and distant to support life as we know it, but its gravitational influence helps stabilize the orbits of the inner planets, preventing chaotic changes that could destabilize the system. The presence of two planets raised an obvious question: could there be more? Scientists began searching for additional worlds, but what they found next wasn't a planet at all. Alpha Centauri A, the brightest star in the system, is about 4 billion years old, similar in age to our Sun. By this stage, any debris disk left over from planet formation should have been cleared away, swept up by planets, or blown out by stellar winds. Yet when Webb pointed its instruments at Alpha Centauri A, it detected warm dust grains orbiting between 1 and 3 astronomical units from the star, the region where rocky planets form. This dust shouldn't exist. After billions of years, collisions and radiation should have removed it, but the dust Webb found wasn't a uniform cloud. It showed distinct bands and gaps as if something was organizing it. The total mass was about 1/20th that of Earth, far too much for leftover debris. Something was replenishing the dust, perhaps through ongoing collisions between asteroids or comets, or even a recent planetary collision. The structure of the dust suggested gravitational resonances, possibly from unseen planets. The gaps appeared at precise distances, hinting at the presence of planets shepherding the dust into rings. Scientists calculated the likelihood of a recent collision, but found no evidence of large debris or thermal anomalies. The disk looked smooth and old, yet it was clearly being maintained by some active process. Another possibility was that Alpha Centauri A had captured material from interstellar space, perhaps a rogue planet or a massive asteroid that was torn apart by tidal forces. The debris would settle into a disk, and the star's heat would warm it, creating the infrared signature Webb detected. This scenario fit the data, but raised new questions about the system's history. The presence of this disk changed the search strategy. If dust orbits Alpha Centauri A between 1 and 3 astronomical units, small rocky planets could be hiding there, lost in the glare. Webb's instruments are sensitive enough to detect them if they transit the star, causing a slight dip in brightness. Scientists scheduled 6 months of continuous monitoring, watching for transits and dips in light. What they found was even stranger. Among the dust, 3 large fragments were moving in retrograde orbits, traveling backward compared to the rest of the system. These objects, each between 50 and 200 kilometers across, glowed in the infrared and followed perfectly circular paths. Natural capture usually creates elliptical orbits, but these were precise circles as if placed deliberately. Simulations failed to explain how 3 objects could end up in such orbits by chance. The probability was vanishingly small. The fragment's composition was ordinary silicates, iron oxides, carbon compounds, but their placement defied natural explanation. They were unique to Alpha Centauri A, with no counterparts around Alpha Centauri B. The mystery deepened. The more Webb observed, the more it found things that shouldn't exist: dust disks around old stars, retrograde fragments in perfect orbits, and planets surviving in chaotic environments. Each discovery forced scientists to reconsider what they thought they knew about how planetary systems form and evolve. And as the data accumulated, it became clear that Alpha Centauri was not just our nearest neighbor, but a laboratory for rewriting the rules of planetary science. The system was more dynamic, more complex, and more surprising than anyone had imagined, and the biggest surprises were still to come. Stars are supposed to follow predictable rules. Their temperature, brightness, and lifespan are all determined by their mass and age. Small stars burn cooler and last longer, while massive stars blaze hot and die young. As stars age, they gradually cool and dim. Alpha Centauri A, by all calculations, should have a surface temperature of about 5,790 Kelvin. But when Webb measured it, the reading came back at 5,940 Kelvin, over 150 degrees hotter than expected. Alpha Centauri B showed a similar anomaly, running about 120 degrees hotter than models predicted. At first, scientists suspected a calibration error, but repeated checks against other stars with known temperatures confirmed that Webb's instruments were accurate. The stars themselves were simply hotter than they should be. This discrepancy might sound minor, but in the world of stellar physics, it's a big deal. Our understanding of how stars work is built on decades of observation and theory. The equations for core fusion, energy transfer, and convection have been tested across the galaxy. For Alpha Centauri A and B to both be hotter than expected, something unusual had to be happening. Three main theories emerged. The first was that the stars were younger than previously thought. Younger stars burn hotter, so if Alpha Centauri A and B were only 4 billion years old instead of 4, that could explain the difference, but every method used to estimate their age, spectral analysis, rotation rates, chemical composition, pointed to the same number, 4 billion years. The second theory involved metallicity. Stars with more heavy elements can burn slightly hotter because the extra metals increase opacity in their outer layers, trapping more heat. But Alpha Centauri's metallicity had already been measured at 1.7 times that of the Sun, and the models accounted for this. The numbers still didn't add up. The third idea was that the stars had recently swallowed fresh material, comets, asteroids, or gas from interstellar space. This would provide extra fuel, temporarily boosting their fusion rates and surface temperatures. The debris disk around Alpha Centauri A supported this idea, as some of the dust could be spiraling inward and being consumed by the star. But Alpha Centauri B didn't have a debris disk, yet it was also running hot. This suggested a shared cause, something intrinsic to the system. One researcher, Dr. Lisa Chen at Princeton, proposed that the binary nature of the system might be responsible. Every 80 years, the two stars swing close together, and the tidal forces could stress their outer layers, generating friction and heat. Mathematical models showed that this could account for a portion of the temperature increase, but not all of it. The rest remained unexplained, a puzzle that hinted at new physics or processes not yet understood. While scientists wrestled with these stellar mysteries, Webb's observations uncovered something even more perplexing. Radio telescopes, working in tandem with Webb's infrared sensors, picked up a narrowband radio signal at 420 MHz, the so-called hydrogen line, a frequency astronomers reserve for studying cold hydrogen in space. Natural sources rarely produce such precise, focused signals. The emission was detected between Proxima Centauri and the Alpha Centauri AB pair, originating from the vast emptiness of interstellar space, not from any star or planet. At first, Dr. Sofia Rodriguez at UC Berkeley thought it was interference from Earth. Satellites often contaminate this frequency, but the signal moved with Alpha Centauri across the sky, ruling out a terrestrial source. The emission lasted for 6 hours, disappeared, then reappeared 3 days later, following a precise pattern. Natural explanations struggled to account for it. Interstellar gas doesn't produce narrowband signals, and plasma instabilities create broad, noisy emissions, not clean, steady tones. The team analyzed the signal for signs of modulation, patterns that might indicate information being transmitted. The signal was a simple sine wave with no obvious message encoded, but the timing was suspicious: 6 hours on, 70, 2 hours off, repeating with clockwork precision. Some scientists suggested cosmic masers, natural radio amplifiers found near star-forming regions, but these are never seen in quiet interstellar space like this. Another theory was that the signal came from a planetary magnetosphere. When charged particles interact with a planet's magnetic field, they can generate radio emissions. Jupiter and Saturn both do this, but to produce a signal this strong and focused would require a magnetic field thousands of times more powerful than Jupiter's. Nothing in the data suggested such a field existed in the Alpha Centauri system. The signal remained a mystery, classified as unidentified. Radio observatories around the world began monitoring Alpha Centauri, hoping for more emissions or changes that might provide a clue. Meanwhile, Webb continued its observations, and what it found next in Proxima B's atmosphere would push the boundaries of what scientists thought possible. On Earth, the coexistence of oxygen and methane in the atmosphere is a sign of life. These gases react with each other and should quickly disappear unless something is constantly replenishing them. On our planet, that something is biology, plants and microbes working in tandem to keep both gases present. Webb's spectroscopy of Proxima b found both oxygen and methane in concentrations that defied chemical equilibrium. Oxygen was present at 400 parts per million, methane at 2 parts per million. According to chemical models, these gases should destroy each other within a century. Their continued presence meant something was actively producing them. The oxygen was particularly puzzling. Most exoplanets with oxygen get it from photolysis, where ultraviolet light splits water molecules and hydrogen escapes to space, leaving oxygen behind. But Proxima Centauri emits less ultraviolet than the Sun, not enough to account for the observed oxygen levels. Methane, meanwhile, is usually produced by either biological or geological processes. On Earth, most methane comes from life, with a smaller fraction from volcanoes and hydrothermal vents. But geological methane is usually accompanied by other gases like sulfur dioxide and carbon monoxide, which Webb did not detect. Scientists considered every possible abiotic explanation: unusual photochemistry, lightning, surface minerals catalyzing reactions, but none could produce the observed ratios. The only process known to maintain such a disequilibrium is life. Still, scientists were cautious. Biosignatures are not proof. They are evidence that demands further investigation. Webb's team scheduled more observations, looking for additional biosignature gases like phosphine, ammonia, or dimethyl sulfide. Each would strengthen the case for life, but what they found next was even more unexpected. A secondary dimming event during Proxima b's transit, suggesting the presence of a large, dark object orbiting close to the star. It was too big and too close to be a moon, and its nature remains a mystery. As the data poured in, the Alpha Centauri system continued to defy expectations. Every observation raised new questions, and the line between natural and artificial phenomena grew increasingly blurred. The search for answers was just beginning, and the implications for our understanding of life and the universe were profound. Brown dwarfs are elusive objects, often called failed stars, because they're too massive to be planets but not quite heavy enough to ignite sustained nuclear fusion like true stars. They are faint, cool, and hard to spot unless you're looking with the right tools. For years, astronomers speculated that Alpha Centauri might harbor such a hidden companion, but the evidence was always just out of reach. The James Webb Space Telescope, with its sensitive infrared detectors, finally provided the clarity needed. During a systematic survey of the Alpha Centauri system, Webb focused on the region between 5 and 50 astronomical units from Alpha Centauri A zone too distant for rocky planets but too close for easy detection from Earth. In this quiet stretch of space, Webb picked up a faint but persistent infrared source about 23 astronomical units from Alpha Centauri A. Its temperature was measured at 100 Kelvin, too warm to be a cold planet, too cool for a star, but just right for a young brown dwarf or a massive planet still radiating heat from its formation. The signal was faint, barely above the background noise, but it appeared in multiple observations. Scientists calculated the object's mass based on its temperature and brightness, estimating it to be between 4 and 8 times the mass of Jupiter. This placed it in the ambiguous category of planetary, mass object, not quite a planet, not quite a brown dwarf, but something in between. The discovery process was meticulous. First, the team had to rule out the possibility that the signal was an artifact of the instrument. Next, they checked whether the object moved through space with Alpha Centauri, confirming it was gravitationally bound to the system. Finally, they eliminated the chance that it was a background star or distant galaxy. All the evidence pointed to a genuine companion orbiting Alpha Centauri A, but this raised a new puzzle. An object this massive should have been detected by previous radial velocity surveys, which measure the tiny wobbles in a star's motion caused by orbiting companions. Alpha Centauri has been studied for decades, and nothing this large had ever shown up. The likely explanation was that the object's orbit was nearly perpendicular to our line of sight, making its gravitational tug invisible to radial velocity methods. Webb, however, could see its heat directly, regardless of orbital orientation. Another factor was the object's long orbital period. At 23 astronomical units, it would take about 80 years to complete a single orbit around Alpha Centauri A. Previous surveys simply hadn't watched long enough to catch its slow movement. The object had been hiding in plain sight, moving so gradually that it escaped notice. The presence of this brown dwarf or planetary mass object complicated the system's dynamics. Now, instead of three main bodies, Alpha Centauri A, Alpha Centauri B, and Proxima, there were four significant gravitational players. Each one tugged on the others, creating a complex web of interactions. Yet, the system remained stable, likely because the new object's orbit was tilted relative to the main binary, reducing the chances of disruptive encounters. This discovery led to speculation that there could be even more hidden companions in the system, perhaps smaller brown dwarfs or massive planets lurking in the darkness, waiting to be found by future telescopes. Meanwhile, Webb's observations of Proxima b continued to yield astonishing results. By capturing the faint light reflected from the planet's surface as it orbited its star, Webb was able to analyze the planet's reflection spectrum. The data revealed a sharp increase in reflected light at wavelengths between 600 and 750 nanometers, a signature that matches the glint of sunlight off liquid water. On Earth, satellites see this effect all the time, the sparkle of sunlight on ocean waves. Dr. Amy Liu at Johns Hopkins led the analysis. This is the clearest evidence for surface oceans we've ever seen on a planet outside our solar system. She said, the reflection pattern, the way the light was polarized, and the specific wavelengths all pointed to large bodies of liquid water. Calculations suggested that between 30% and 70% of Proxima b's dayside was covered by oceans, but this raised another question. On a tidally locked planet, the dayside is constantly exposed to the star, while the night side is in perpetual darkness. Water should evaporate from the hot dayside, rise into the atmosphere, and eventually freeze out on the night side, leaving the dayside dry and barren. Yet, Proxima b maintained liquid water on its sunlit hemisphere. Somehow, water was cycling back from the night side, creating a stable hydrological cycle. The answer seemed to lie in the planet's atmosphere. Winds and weather systems transported moisture from the dayside to the night side and back again. The terminator, the boundary between day and night, was likely the most temperate region, with both liquid water and ice present. Webb detected temperature variations and cloud formations at the terminator, evidence of active weather patterns. Convection cells rose from the warm ocean, while cold fronts descended from the night side, creating a dynamic climate unlike anything seen on Earth. The presence of liquid water elevated Proxima b from potentially habitable to actually habitable. Water is the key ingredient for life as we know it, and its presence, combined with a stable atmosphere and magnetic protection, made Proxima b the most promising candidate for life beyond our solar system. But scientists remained cautious. Indicators of habitability are not the same as proof of life. They needed definitive biosignatures, gases, or molecules that could only be produced by living organisms. The atmospheric data provided tantalizing hints, but the search for unambiguous evidence continued. Webb's next observations focused on seasonal changes. On Earth, seasons are caused by the planet's axial tilt, but Proxima b, being tidally locked, shouldn't have seasons in the traditional sense. Yet, over 3 months of continuous monitoring, Webb detected temperature shifts. The day side cooled by 12 Kelvin, the night side warmed by 8 Kelvin, and atmospheric pressure at the terminator increased by 15%. Wind speeds doubled at certain latitudes. Something was driving these cycles. Dr. Marcus Flynn at MIT proposed that Proxima b's slightly elliptical orbit was the cause. Even a small eccentricity would change the planet's distance from its star, altering the amount of radiation it received. Calculations showed that Proxima b's orbit varied by about 1.2 million kilometers, enough to change incoming energy by 30%. This created seasons on an 11-day cycle with rapid shifts in climate and weather. The planet's response was remarkable. During close approach to the star, evaporation increased, clouds formed, and more sunlight was reflected back into space, a natural thermostat. During the more distant part of the orbit, clouds dissipated, the ocean absorbed more heat, and temperatures stabilized. The feedback systems suggested a planet capable of self-regulation, maintaining stability despite external changes. These rapid orbit-driven seasons affected not just temperature, but also atmospheric chemistry. Oxygen levels peaked during close approach, while methane concentrations rose during the cooler phase. The variations were too strong to be explained by chemistry alone. They hinted at biological processes responding to environmental changes. The evidence was mounting, but the most startling discoveries were still ahead. Webb's instruments were about to reveal something that would challenge everything scientists thought they knew about life in the universe. Gamma-ray bursts are among the most violent and energetic events in the universe. They're usually the result of massive stars collapsing into black holes or neutron stars colliding, releasing a flash of radiation that can outshine entire galaxies for a few seconds. These bursts are almost always detected in distant galaxies billions of light years away. So when, on March 17, 2024, NASA's Fermi Gamma-ray Space Telescope picked up a short burst from the direction of Alpha Centauri, astronomers were stunned. The burst lasted just over 4 seconds, with an energy profile that didn't match any known local event. It seemed to come from behind Proxima Centauri, not from the star itself, but from the empty space between Proxima and the Alpha Centauri binary, coincidentally, the same region where the mysterious radio signal had been detected months earlier. The scientific community mobilized instantly. Observatories around the world turned their attention to Alpha Centauri, hoping to catch an afterglow or some sign of a supernova. The James Webb Space Telescope interrupted its schedule to gather infrared data, searching for any heat signature or expanding debris, but nothing appeared. The region remained as dark and unchanged as before. Whatever caused the gamma-ray burst left no visible trace, no explosion, no shockwave, no lingering light. It was as if the burst had simply materialized and vanished, leaving only questions in its wake. Dr. Kevin Zhang at Caltech analyzed the burst's energy spectrum and timing. It didn't fit the profile of a collapsing star or a magnetar flare. Instead of a single smooth pulse, the burst had 3 distinct peaks, each separated by a fraction of a second. The pattern looked almost artificial, as if it had been engineered rather than produced by random cosmic violence. The idea was unsettling, but the data forced scientists to consider possibilities they'd never imagined. Radiation from the burst reached Proxima b about 25 seconds after it was detected on Earth due to the geometry of the system. Webb watched as the planet's atmosphere absorbed the energy. The upper layers heated rapidly, electrons scattered, but within minutes the atmosphere stabilized. The planet's magnetic field and thick air had shielded the surface from harm. Proxima b had survived yet another cosmic assault, seemingly built to endure the universe's worst. Theories about the burst's origin ranged from the plausible to the extraordinary. Some suggested a previously unknown type of natural event, while others whispered about artificial causes, perhaps a signal, a test, or a demonstration of technology far beyond our own. But with no repeat event and no physical evidence left behind, the mystery remained unsolved. Meanwhile, Proxima Centauri itself continued its unpredictable behavior. Red dwarfs are notorious for their flares, and Proxima is no exception. Every few weeks, it erupts with a blast of X-rays and ultraviolet light, increasing its brightness by up to 25%. These flares are powerful enough to sterilize the surface of any unprotected planet in seconds. Over 8 months, Webb recorded a dozen such flares, each one a test of Proxima B's resilience. During a particularly strong flare in June 2024, the planet was bombarded with 700 watts per square meter of high-energy radiation concentrated in the most dangerous wavelengths. Earth receives about twice that from the Sun, but spread across the full spectrum. Proxima B's exposure was focused and deadly. The planet's magnetic field responded instantly, compressing on the day side and stretching on the night side, forming a protective bubble. Charged particles were funneled toward the poles, creating auroras that glowed in the infrared, visible to Webb's sensors as green and red light from excited oxygen molecules. The upper atmosphere heated rapidly, molecules broke apart, and chemistry was thrown into chaos. Water vapor split into hydrogen and oxygen, carbon dioxide into carbon monoxide and atomic oxygen. But the lower atmosphere remained stable, and the surface temperature barely changed. Within hours, the atmosphere reassembled itself, water vapor returned, and oxygen levels stabilized. Proxima B's environment had evolved to survive, recover, and adapt to these relentless assaults. Dr. Patricia Moore at Oxford calculated that over its lifetime, Proxima B has endured roughly 10 million such flares. Each one could have been catastrophic, yet the planet's systems, magnetic, atmospheric, and perhaps even biological, had developed ways to absorb the damage and repair themselves. On Earth, life evolved enzymes to fix DNA damage, antioxidants to neutralize free radicals, and strategies to survive extreme conditions. If life exists on Proxima b, it must be even more robust, with mechanisms to withstand a far harsher environment. But the planet's toughness wasn't the only thing that caught scientists' attention. Webb's high-resolution mapping of the terminator, the twilight ring between day and night, revealed a pattern that defied natural explanation. The terminator is the most stable region on a tidally locked world, with temperatures hovering just below the freezing point of water. Here, Webb detected a series of evenly spaced hotspots, each about 50 kilometers in diameter and 5 Kelvin warmer than their surroundings. There were 30 in total, arranged in a near-perfect grid around the planet. Dr. Hannah Lee at Stanford led the analysis. "This isn't random," she said. "It's too organized for geology, too regular for weather." On Earth, volcanic hotspots cluster along tectonic boundaries, and atmospheric convection cells drift and merge. But Proxima B's hotspots were fixed, unchanging, and perfectly spaced. The energy output was modest, about 1 megawatt per spot, but the pattern suggested purpose, not chance. Alternative explanations were considered. Could these be volcanic in origin? Unlikely, given their distribution. Hydrothermal vents? Possible, but vents don't arrange themselves in grids. Atmospheric phenomena. Convection cells don't stay fixed for months at a time. The only thing left was the possibility of artificial origin, structures or systems designed to generate heat in specific locations. The idea was controversial, and scientists were careful not to jump to conclusions. The hotspots were officially classified as anomalous thermal features, confirmed but unexplained, yet the regularity and persistence of the pattern nagged at everyone who studied the data. If these were natural, they were unlike anything seen before. If they were artificial, they hinted at a level of organization and technology that would change everything we know about life in the universe. As the debate raged, Webb's instruments continued to gather data, searching for the next clue that might tip the balance from mystery to understanding. The evidence was building, and the world waited for the next revelation from our nearest neighbor. Phosphine is a molecule that shouldn't last long in an oxygen-rich atmosphere. On Earth, it's produced almost exclusively by life, anaerobic bacteria in swamps, microbes in animal guts, and a few industrial processes. When exposed to oxygen, phosphine quickly oxidizes and vanishes unless something is constantly making more. So when Webb detected phosphine on Proxima b, not just in trace amounts, but at a strong, clear signal of 20 parts per billion, it sent a ripple of excitement and skepticism through the scientific community. The spectral lines were unmistakable, confirmed across multiple observations, and always accompanied by oxygen in the same atmospheric layers. Dr. Samuel Brooks at Yale led the effort to rule out non-biological sources. Lightning, volcanic gases, and photochemistry were all considered. Models showed that even the most generous geological or chemical processes could only account for a fraction of the observed phosphine, no more than half a part per billion. The measured concentration was 40 times higher. The gap between theory and observation was too wide to ignore, but phosphine wasn't the only surprise. Webb also found dimethyl sulfide, a gas on Earth produced almost entirely by marine phytoplankton at 5 parts per billion. Then came methyl chloride, another molecule associated with biological activity, especially from plants and algae. Each of these gases could, in theory, be produced by exotic chemistry, but the odds of all three appearing together in the observed ratios by non-biological means were vanishingly small. The ratios themselves told a story. On Earth, the balance of oxygen, methane, phosphine, and other trace gases is shaped by the metabolism of living things. Seasonal changes affect the numbers, but the underlying relationships remain stable. Proxima B's atmosphere showed similar patterns, not identical, but close enough to suggest a comparable web of biological processes cycling elements through the air and possibly the oceans. Skeptics argued for unknown chemistry. After all, exoplanet atmospheres are still a new frontier, and it's possible that processes we haven't discovered could explain the data. But as more observations came in, the case for biology grew stronger. Each new spectrum reinforced the same message. Something on Proxima b was maintaining a chemical disequilibrium that on Earth only life can sustain. The debate reached a fever pitch in the summer of 2024. Conferences devoted entire sessions to Proxima b. Papers poured into journals, each proposing new models or challenging old ones. Some researchers clung to the hope of exotic chemistry, while others began to accept that the simplest explanation might be the right one: life. Then, in August, Webb observed something that made the bio-signatures seem almost routine by comparison. During a routine transit, as Proxima b passed in front of its star, the expected dip in brightness occurred. But this time, there was a second, smaller dip 3 hours after the main event. It lasted just 17 minutes and was much shallower, but it was real, confirmed across multiple instruments and repeated in subsequent transits. Initial calculations suggested the object responsible was about 1,500 kilometers in diameter, roughly the size of our moon. But it couldn't be a moon. Tidal forces so close to a red dwarf would tear any natural satellite apart in a few million years. Nor could it be a ring system, as the dimming was too sharp and brief. The object seemed to orbit extremely close to the star, in a region where only the densest, most heat-resistant materials could survive. Spectroscopy during the secondary trance, it revealed nothing, no atmosphere, no reflected light, just a clean, featureless shadow. Dr. Rachel Foster at Yale proposed a brown dwarf hypothesis, but the mass required for such an object would have caused Proxima to wobble far more than observed. Others suggested a debris cloud or a swarm of asteroids, but the regularity and sharpness of the event argued against it. The mystery object became known as Proxima's shadow. It was massive, dark, and persistent, orbiting in a way that defied easy explanation. Every transit brought the same pattern: main event, 3-hour gap, secondary dip, always the same duration and depth. The regularity suggested something stable and long-lived, but its nature remained elusive. While astronomers puzzled over Proxima's shadow, attention shifted back to Alpha Centauri A. Brown dwarfs are notoriously difficult to detect, but Webb's deep infrared scans revealed a faint source at 23 astronomical units from the star. Its temperature and luminosity placed it in the gray area between planet and brown dwarf, with a mass estimated at 4 to 8 times that of Jupiter. The object's slow, wide orbit explained why it had escaped detection for so long. The presence of this companion complicated the gravitational dynamics of the system. With 4 major bodies, Alpha Centauri A, Alpha Centauri B, Proxima, and the new brown dwarf, the system was more crowded and complex than previously thought. Yet, stability analyses showed that the orbits were arranged in such a way as to avoid close encounters, with each object moving in its own plane, like dancers in a cosmic ballet. Webb's observations also revealed something remarkable about Proxima B's surface. By analyzing the light reflected from the planet during different phases of its orbit, scientists detected a sharp increase in brightness at certain wavelengths, a signature of liquid water. The effect, known as ocean glint, is familiar from Earth, where sunlight reflects off the waves at just the right angle. Calculations suggested that a significant portion of Proxima B's dayside was covered by oceans, with the terminator region, the boundary between day and night, likely hosting the most stable and temperate conditions. But maintaining liquid water on a tidally locked planet is no small feat. The dayside should be a boiling cauldron, the night side a frozen wasteland. Yet, Proxima B's atmosphere and ocean currents seemed to work together to transport heat and moisture, creating a dynamic, self-regulating climate. Clouds formed and dissipated, storms raged along the terminator, and water cycled between liquid and ice, defying the simple models that once predicted a barren world. The evidence for habitability was overwhelming. Magnetic protection, a stable atmosphere, surface oceans, and a suite of signature gases all pointed to a living world, but scientists remained cautious, knowing that extraordinary claims require extraordinary evidence. The search for definitive proof continued, with every new observation bringing humanity closer to answering the age-old question, are we alone? As the months passed, anticipation grew. The world watched as the James Webb Space Telescope continued its vigil, peering across the void at our nearest neighbor, waiting for the next piece of the puzzle to fall into place. The search for life is a process of elimination, of ruling out the ordinary until only the extraordinary remains. By late 2024, the evidence from Proxima B was stacking up in ways that made skepticism harder to maintain. Dr. Robert Chen at Harvard compiled a comprehensive analysis weighing each signature, oxygen, methane, phosphine, dimethyl sulfide, methyl chloride, and the presence of surface oceans. Even if each had a 90% chance of being produced by non-biological means, the odds of all five appearing together by chance dropped below 1%. The statistical case for life was becoming overwhelming, even if absolute proof remained elusive. The implications of such a discovery rippled far beyond the scientific community. If life existed just 4 light years away, the odds of it being common throughout the galaxy skyrocketed. The Drake equation, once a speculative tool, suddenly had a data point close to home. If our nearest neighbor harbored life, then the universe might be teeming with it, billions of worlds, each with its own evolutionary story. Religious and philosophical circles responded in their own ways. Some saw confirmation of a universe filled with purpose. Others struggled to reconcile the news with long-held beliefs. Political leaders convened quiet meetings, debating whether to send a message, how to prepare for the possibility of contact, and what it would mean for humanity's place in the cosmos. Committees formed, protocols were reviewed, and the world's space agencies began to plan for the next steps. Public interest exploded. Social media buzzed with speculation, hope, and anxiety. People wanted answers immediate, definitive, and simple. Scientists tried to explain the nature of evidence, the difference between high confidence and certainty, but nuance was often lost in the noise. The possibility of neighbors in the next star system was too profound to be contained by cautious language. Space agencies responded with ambition. NASA proposed a fly-by mission using solar sail technology, aiming for a launch in 2030 and an arrival by 2070. The European Space Agency countered with a laser-pushed light sail, hoping to cut the travel time to just 20 years. China announced its own classified program, fueling a new kind of space race. The idea of reaching Proxima B within a human lifetime was no longer science fiction, it was a goal within reach. But while plans for interstellar probes took shape, the need for more immediate answers remained. The James Webb Space Telescope, with its unique vantage point and sensitivity, became the world's primary tool for monitoring Proxima b. Every new observation was scrutinized for signs that could tip the balance from likely to certain. Then, in early 2025, something happened that forced the scientific community to act. The Very Large Array, a network of radio telescopes in New Mexico, detected a narrowband signal from Proxima b during a planetary transit. The frequency, 420 MHz, was the same as the earlier mysterious signal, but this time it was stronger, more structured, and lasted exactly as long as the planet's transit across its star. The odds of such a coincidence were minuscule. The radio team sent out an urgent alert, and within hours, Webb was redirected to observe Proxima b's atmosphere during the next available transit. Dr. Sarah Martinez at the SETI Institute led the analysis. "This isn't random plasma noise," she reported. "There's a pattern, frequency shifts, modulations, a structure that looks like information. The signal repeated every 30 seconds, rising and falling in frequency in a way that suggested intentional encoding. Attempts to decode the signal began immediately. It didn't match any known human communication protocol, nor did it resemble natural radio emissions from planets or stars. The structure was too organized, the timing too precise." The scientific community split into camps, one arguing for a natural explanation, the other for a deliberate transmission. The debate quickly became political, with some calling for an immediate response and others urging caution. International organizations, including the United Nations, convened emergency sessions to discuss protocols for potential contact. Who would speak for Earth? What should be said? What risks might there be in responding? The questions were unprecedented, and the answers were anything but clear. Meanwhile, Webb continued its observations, searching for any atmospheric changes that might correlate with the radio signals. In March, another signal was detected, same frequency, same pattern, but this time lasting 8 minutes. Computer analysis showed the signal contained 4 bits of information per symbol, complex enough to carry a message, but not so complex as to rule out a natural origin entirely. The ambiguity was maddening. The implications were staggering. If the signals were artificial, then someone on Proxima b knew we were watching. They would have seen our radio and television broadcasts, our radar pings, our growing curiosity. The light from Earth takes just over 4 years to reach Proxima Centauri, so any response would be delayed by at least that long. The possibility of a cosmic conversation, even at such a slow pace, was enough to capture the imagination of billions. Economic and cultural impacts began to ripple through society. Funding for space exploration surged. Private companies invested in propulsion technologies that had once seemed fanciful. Literature, film, and art grappled with the new reality, imagining first contact scenarios and the challenges of understanding a truly alien civilization. Children grew up learning that life might exist just next door and that humanity was no longer alone in the universe. But for all the excitement, the scientific community remained focused on the data. Each new observation was a piece of a puzzle that, when complete, would answer one of humanity's oldest questions. The search for life on Proxima b was no longer just a scientific endeavor. It was a global project, a shared journey into the unknown. And as the James Webb Space Telescope continued its watch, the world waited for the next signal, the next clue, the next step toward understanding our place in the cosmos. Atmospheres on planets usually change at a glacial pace. On Earth, oxygen levels took hundreds of millions of years to reach their current state, and even seasonal shifts in carbon dioxide are measured in tiny increments over decades. Venus's toxic clouds have remained stable for billions of years. But Proxima b was different. In June 2025, Webb captured a continuous 12-hour spectroscopic sequence of the planet's dayside. The first readings were as expected: oxygen at 400 parts per million, methane at 2 parts per million, water vapor at 7 parts per thousand. But 6 hours later, the numbers had shifted dramatically. Oxygen had jumped by 30%, methane had dropped by the same proportion, and water vapor remained steady. Dr. Elizabeth Park at Princeton was the first to suspect a calibration error. She ran diagnostics, checked for temperature drift in the sensors, and requested independent verification from other observatories. But every check confirmed the same thing. The atmosphere of Proxima b was changing in real time on a timescale of hours, not millennia. The team searched for a trigger. Was there a solar flare? No, Proxima had been quiet for over a week. Was the planet at a special point in its orbit? No, it was at an average distance from its star. The only clue was a slight cooling of the dayside by 4 Kelvin during the shift. Normally, oxygen production requires energy input. Photosynthesis on Earth uses sunlight, and photolysis uses ultraviolet. But here, oxygen increased while the temperature dropped, suggesting energy was being absorbed for some other process. The methane decrease made sense in the context of rising oxygen as the two gases react and destroy each other, but the speed of the change was too fast for chemistry alone. It was as if something had stopped producing methane or started producing oxygen in response to a signal. The atmosphere then gradually returned to its baseline over the next 14 hours, as if the planet had reset itself. This kind of coordinated, reversible change didn't match any known geological or meteorological process. Volcanoes don't pulse their gas output on 12-hour cycles. Weather patterns don't create such precise chemical swings. Even biological processes on Earth are messier, with more noise and less regularity. Proxima b's atmosphere seemed to be managed, as if by a global system responding to environmental cues. Calculations showed that the 30% oxygen increase meant an extra 50 tons per second being released into the air, an enormous amount, requiring either massive biological productivity or some unknown process. The scale and precision of the change were both unsettling and intriguing. Follow-up observations revealed that these shifts weren't isolated events. In July, 3 more were recorded. In August, 5. Each lasted 10 to 14 hours, always following the same pattern: oxygen up, methane down, temperature drop, then a return to normal. The regularity suggested cycles or rhythms, perhaps tied to the planet's orbit or some internal clock. Meanwhile, Webb's auroral observations provided a new window into Proxima b's magnetic field. On Earth, the magnetic field varies only slightly with solar activity, but Proxima b's field strength fluctuated between 3 and 6 times that of Earth, with patterns that didn't match any obvious external cause. Dr. Ahmed Hassan at Cambridge noticed that every spike in magnetic field strength coincided with a radio signal from the planet. The correlation was nearly perfect. 97% of the time, a magnetic spike was followed by a radio emission within minutes. This suggested that the magnetic field wasn't just a passive shield, but was being actively modulated, perhaps to generate the radio signals. On Earth, moving magnetic fields create electric currents, which in turn can produce radio waves. But controlling a planetary magnetic field on this scale would require technology or biology far beyond anything known. 3 scenarios were considered. The first was artificial structures in the upper atmosphere, giant coils or conductors generating local fields. The second was direct manipulation of the planet's core, somehow altering the convection patterns that drive the dynamo. The third, and most radical, was that life itself was responsible, perhaps a global network of magnetotactic organisms coordinating to produce field changes. To test the predictive power of the correlation, NASA approved a dedicated observation campaign. For 3 months, Webb and ground-based radio telescopes watched for magnetic spikes, and in 8 out of 9 cases, a radio signal followed within minutes. The 9th time, the field spiked but no signal appeared, perhaps a failed transmission or a change in plans. This level of organization was unprecedented. Natural processes rarely produce such tight synchronization. Weather and tides on Earth are only loosely correlated. Even biological cycles have more variability. The implication was that something on Proxima b was deliberately controlling both its magnetic field and its radio emissions. At the same time, Webb's higher resolution spectroscopy revealed another surprise: the presence of complex organic molecules in the atmosphere. Glycolaldehyde, acetaldehyde, and formamide, molecules that on Earth are associated with prebiotic chemistry and the building blocks of life, were all detected in significant concentrations. These molecules don't last long in oxygen-rich air. Their presence meant they were being constantly produced. On Earth, glycolaldehyde is a simple sugar, a precursor to RNA. Acetaldehyde is produced by the oxidation of alcohol, often as a byproduct of fermentation. Formamide is crucial for the formation of nucleotides and peptide bonds. The ratios of these molecules and their persistence in the atmosphere suggested active synthesis, not random chemistry. Lightning and ultraviolet light can create complex organics, but they usually produce a messy mix of hundreds of compounds. Webb's data showed a selective chemistry, with just a few key molecules appearing in the right proportions. Volcanic and hydrothermal processes were also considered, but these would produce sulfur compounds, which were absent from the spectra. The synthesis was becoming clear. Proxima B's atmosphere was not just habitable, but alive with activity, chemical, magnetic, and possibly biological. The planet's systems were coordinated, responsive, and complex, hinting at a level of organization that went beyond simple life. The world waited for the next observation, the next anomaly, the next piece of evidence that might finally tip the scales from possibility to certainty. And as the data accumulated, the sense grew that humanity was on the verge of the most profound discovery in its history. 17 months of relentless observation, hundreds of spectra, dozens of transit measurements, and nearly 100 radio signal detections, all of it pointed to a single, inescapable conclusion. By October 2025, the world's scientific community was on edge, waiting for the next breakthrough, the next anomaly, the final piece of evidence that would transform speculation into certainty. The James Webb Space Telescope, along with ground-based observatories and radio arrays, had amassed a mountain of data. Every new finding seemed to reinforce the same message. Proxima b was not just habitable, but inhabited and perhaps even home to intelligence. On October 27, 2025, the world paused as NASA, the European Space Agency, and their international partners called a joint press conference. Security was tight, rumors swirled, but no one outside the inner circle knew what was about to be announced. When Dr. Rachel Morrison stepped to the podium, her words were simple and direct. The James Webb Space Telescope has detected unambiguous evidence of life on Proxima Centauri B. The room erupted, cameras flashed, questions flew, but she waited for silence before continuing. We have also found evidence consistent with technological civilization, biosignatures, atmospheric management, organized surface structures, and repeated communication attempts. We are not alone. Our neighbors live just 4 light years away. The evidence was laid out methodically. Impossible concentrations of biosignature gases, atmospheric composition that changed in real time, a magnetic field that was not just strong but actively modulated, radio signals synchronized with those magnetic changes, and complex organic molecules that pointed to advanced chemistry. The thermal anomalies, 30 evenly spaced hotspots along the terminator, were confirmed as persistent, organized, and inexplicable by natural processes. Orbital structures, seen as anomalies during planetary transits, suggested the presence of large, stable objects in precise orbits. Every piece of data had been checked, rechecked, and verified by independent teams. The probability of all these phenomena occurring naturally was less than 1 in a billion. The confidence level exceeded the standard for scientific discovery by orders of magnitude. But the most compelling evidence came just days before the announcement. On October 15th, Webb detected a new radio signal from Proxima b, this time at 1,667 MHz, the hydrogen line, a frequency universally recognized by astronomers as a logical choice for interstellar communication. The signal was not continuous, but pulsed 30, 1 bursts, a pause, then 30, 1 more. The sequence repeated, a prime number, a mathematical signature that could not be produced by chance. It was the classic demonstration used in SETI protocols, a way of saying hello across the void. The signal was focused, aimed directly at Earth, as if in response to our decades of searching and listening. The scientific community responded with careful language. Signature replaced alien civilization. Organized biosignatures became managed ecosystem. Potential communication attempt was the phrase used instead of they said hello, but the meaning was clear. Life existed on Proxima B, intelligence existed, technology existed, and they knew we were watching. Governments activated emergency protocols. The United Nations convened in special session. Religious leaders issued statements, some welcoming the news, others urging caution. Philosophers and ethicists debated the implications. Who would speak for Earth? What should we say? How do you introduce yourself to a neighbor you've never met, whose language, biology, and history are utterly alien? The public reaction was a mix of awe, excitement, fear, and hope. Some celebrated, some worried, some denied, but most simply marveled at the enormity of the discovery. The universe, once thought vast and empty, was now revealed as populated, alive, and perhaps even welcoming. Plans for interstellar missions accelerated. Laser sail probes, nuclear propulsion concepts, and even more exotic ideas received funding and international support. The first launches were scheduled for the 2030s, with the hope that the people who witnessed the discovery might live to see the first close-up images of Proxima B, or even the first direct contact. Meanwhile, Webb and other observatories continued their watch. Every day brought new data, atmospheric readings, radio signals, thermal maps, and more. The planet's atmosphere was tracked in real time, its radio emissions monitored continuously, its surface studied for any sign of change. The world's attention was fixed on a tiny point of light in the southern sky, a place that had gone from a distant curiosity to the most important address in the galaxy. The implications rippled through every aspect of human life. Science shifted from searching for life to understanding alien biology. Philosophy and religion adapted to a new reality. Politics and economics were transformed by the prospect of contact, cooperation, or competition with another civilization. Children grew up knowing that humanity was not alone, that the universe was filled with possibilities, but for all the excitement, the discovery brought new questions. What kind of life existed on Proxima B? Was it microbial, multicellular, or something entirely different? What was the nature of their technology? How did they survive the violence of their star, the challenges of a tidally locked world, the constant bombardment of radiation? And most importantly, what would they think of us? The first message from Proxima B was simple, mathematical, and universal. But what would come next? Would they send more complex signals, images, or even a language? Would they wait for a reply or continue their own observations as cautious and curious as we were? The conversation had begun, but its future was unwritten. The search for life had changed humanity forever. The discovery of neighbors just 4 light years away forced us to confront our place in the cosmos, to rethink our assumptions, and to imagine a future filled with new possibilities. The journey was only beginning. The universe, once silent, had spoken, and now it was up to us to answer. As the world looked up at the night sky, at the faint red glow of Proxima Centauri, everyone knew that the greatest adventure in human history had just begun. The distance between stars was no longer an unbridgeable gulf, but a challenge to be met, a path to be traveled, a story to be written together with whoever was waiting on the other side.